Hello, welcome to my channel. Now in this video, we want to find the greatest integer which is less than or equal to the sum of these two integrals, right? So we have the integral from 1 to 2 of this function, and then the integral from 1 to logarithm of 9 to base 2 of this part, right? Okay, so our result will be an integer if the sum of these two functions is an integer, but our result will be an integer, the greatest integer less than the sum of these two functions if the sum of these two functions gives us a decimal number. For example, if we are given 5.1 as a result after adding these two together, then we are to return just 5 because 5 is the greatest integer less than 5.1. All right, okay, great. So let's see what we have. We are given this. Let's start with this integral here. So we have the integral from 1 to logarithm of 9 to base 2 of this here, which is 2 to the power x minus 1, right? Then we raise that to power 1/3 dx. Well, we want to start off with a substitution. I'm going to make a u sub there, and I'm going to say u to be the inside, but not just u to power 3. The reason is this is 1/3, that is a cube root, all right? So if we raise it to power 3, if we raise this input, or if we can make this input a perfect cube, we can cancel out with the cube root. So, and that will work, isn't it? So we say let u to power 3 will be 2 to the power x minus 1. Okay, so that's it. So 2 to the power x minus 1, we replace it with the cube, with a perfect cube. So let's differentiate this and see what we have. Well, we differentiate this with respect to x, we're going to have 3u squared du. Okay, and let's put the dx on the right hand side. But differentiating this with respect to x will give us 2 to the power x times the natural logarithm of 2, all right? Okay, so this is just a constant, so we have x here. All right, that's nice, isn't it? So let's do the substitution and see. So this will become the integral. Well, this is 1 in terms of x. We want to change it to the u variable. So when x is 1, let's see what u will be. When x is 1, that will just be u cube will be equal to 1. That means u must be 1. Okay, that's nice. Now when x is logarithm of 9 to base 2, let's see what u will be. Logarithm of 9 to base 2 is here, and then the base of that is just 2. So by logarithmic properties, we are just going to have 9 left. 9 minus 1 will be 8. U has to be 2 because 2 to the power 3 gives us 8. Okay, that's nice. So remember, this place is what we called u, 2 to the power x minus 1. We raised 2, we didn't call it u, we called it u to the power 3. Then you take the cube root of that, so u is going to be left there. And then the dx. Well, making dx subject of formula here means we're going to divide both sides by this term here. That is 2 to the power x times the natural logarithm of 2. So we're going to have 3u squared. When we put the du here, we divide it by 2 to the power x times the natural logarithm of 2, all right? So let me put the natural logarithm of 2 here. Take note, we want to make everything to be in terms of u, all right? So that's why I don't want to write something in terms of x. But we can make a replacement for this 2 to the power x, given that from here 2 to the power x can be written as u to the power 3 plus 1. So I'll make that here. That will be u to the power 3 plus 1. Okay, that's nice. So we are done making the change of variable. And now let's see what we have. Well, you notice that this integral, this is just 1 over natural logarithm of 2, so maybe just keep that. Well, notice something. This right here, the derivative of this function, the derivative of this denominator here, gives us the numerator. Very nice, isn't it? U to the power 3 plus 1, the derivative of that will just be 3u squared. So if we want to integrate this thing, we just have natural logarithm of the denominator, since the derivative of the denominator gives us the numerator, given that this thing will be taken out of the integral sign. And this u is here. But well, what will we do integration by part? Differentiate u and then integrate this part, all right? It will make the work a little bit easier. So let's just go ahead and do that. So you put the d here, we put the I here, we put the addition sign, the subtraction sign here. Okay, so by integration by part, I'm going to set it up this way. You can watch black pen, red pens videos to get on with it, all right? So first of all, I'm going to put down the function we want to differentiate, which is the u, and then I'm going to put down the function we want to integrate, which is 3u squared divided by, let me put the natural logarithm of 2 here, but you multiply it by 1 plus u to the 3rd power, all right? Okay, that's nice. So we differentiate this u with respect to u. We are going to have 1 with respect to u, all right? We integrate this function. As I said, this is just a constant multiple, so we can take it out, okay, and then deal with this. The integral of this function, this part here, will just give us natural logarithm of the base. So we multiply by this natural logarithm of 2. That will be natural logarithm of 2, 1 over natural logarithm of 2, okay, times the natural logarithm of the base, that is natural logarithm of the denominator, not the base, the denominator. 1 plus u to the power 3. Okay, that's very nice, isn't it? So you just check that out. So that's just by applying the DI method. But we need to take our result out. This here, we are going to multiply this diagonal and then multiply the last row and integrate it. That is, we integrate the product of the last row. So let me just put that down here. Okay, let me put it down here for you to see what we mean. So we multiply this with that. We're going to have this time that will be u over the natural logarithm of 2, right? ln of 2. Okay, then the natural logarithm of this term, which is 1 plus u to the power of 3. Then we subtract negative, right? Negative 1 times this. That will be negative of the integral of that. Remember, we will multiply this last row and then integrate it. So that will be 1 over 2 times that. That will be natural logarithm of 1 plus u to the 3rd power. We divided by the natural logarithm of 2. Okay, and then we have to put the du here. And remember the bounds of integration. This was from 1 to 2. Okay, we put it here from 1 to 2. So let me just put the 2 here. Anyway, let me clean from the top, right, to the second to the last line so that we see what we are actually doing inside there. Okay, so putting this up here, this is what we have, right? Just that I've written it. This natural logarithm of 2 is directly under the natural logarithmic function there, and then the integral is just written as it was, right? Okay, so let's see what we have. Well, you notice something. By change of base of logarithmic properties, all right, this is logarithm to base e and logarithm to base e. We can rewrite that a little bit by changing the base to logarithm of that. Let me show you what I mean. This will become the logarithm to base 2, all right? That is, this entry here can become the new base, and then the original input still stays the same. Okay, that's just from change of base of logarithms anyway. So this is from 1 to 2. Then we are going to do the similar thing to this inside function. This will become, we change the base to base 2, right? That will become the logarithm to base 2 of this input, which is 1 plus u to the 3rd power. And then we put the du over here. Okay, that's nice. So let's evaluate this and see what we have. Well, when u is equal to 2, we substitute 2 in place of u. We are going to have 2 here. So let me put it here, 2 times, right? So we put it here, 2 times logarithm to base 2 of, well, 2 is here, 2 to the power 3 will just be 8, and then we add 1 to that, that will be 9. All right, and then we are going to subtract, substitute 1, that will be 1 here, then the logarithm of, well, this is going to be 1 plus 1, that will just be 2. In fact, logarithm of 2 to base 2 will give us 1, so this place is just 1, all right? So that is the first part. Then we are going to look at this integral. But notice something here. This is integral from 1 to 2 of, now, look at this part, all right? This is integral from 1 to 2 of logarithm to base 2, logarithm to base 2 of 1 plus x to the 3rd power, 1 plus u to the 3rd power, dx, and then du. So the only difference between this and that is just in the variable. And good enough, since this is a definite integral, these variables are just dummy variables. So I can change this from u to x, right? Okay, so let me just show you what I mean. This is going to be the logarithm to base 2 of 1 plus x to the 3rd power, right? Then dx. I'm just changing the variable because they are dummy variables. You can use whatever you want. The result still stays the same. Okay, so doing that, notice that the integral we were working with was this one, and it gives us this difference here, this one minus that. So putting this one back here, we are going to see that this will cancel out with that because they're exactly the same thing. This is just a dummy variable, so you can put whatever you want. I can put here, I can put y, I can put whatever. I can even cancel it without changing it. It means the same thing. So that means what we have left is just this part, which is 2 times the logarithm of 9 to base 2, right? Logarithm of 9 to base 2. So after cancelling those things, the thing has been simplified to this form without the integral. That's the nice thing here. The integral is no longer there, so we don't have to evaluate anything again. So we just have to look at this number. Remember, the results, the question demands to us to find the greatest integer, which is less than or equal to the sum of these two integrals. The sum of these two integrals gives us this. So we need to know what number this is, all right? So in fact, notice something. This right here is logarithm of 9 to base 2. logarithm of 9 to base 2, right? 2 times that. Well, logarithm of 9 to base 2 is bigger than 3. The reason is logarithm is an increasing function, right? So if now we know logarithm of 8 to base 2 to be 3. Logarithm of 8 to base 2, that is just 3, right? So since it has been increased to 9, then the result from this one will be bigger than the other one because logarithm is an increasing function. So in fact, this will be bigger than 3. So maybe I can put 3 here on the left hand side and say 3 is less than the logarithm of 9 to base 2, alright? But this 9 here is not big enough. In fact, if this 9 is up to 12, then the result will be up to 3.5, so also to say. But in fact, this right here is less than 3.5. Okay, that's nice. Now notice something. We need to look at we need to know what 2 times logarithm of 9 to base 2 will be. So if you multiply through by 2, we are going to have 2 times this, right? Okay, so multiplying the left hand side by 2, or the extreme left hand side by 2, we're going to have 6. Multiplying the extreme right hand side by 2, we are going to have 7. But here we need to subtract 1, alright? I'm just trying to find the bound of this number. So subtracting 1 from 6, we are going to have 5. And subtracting 1 from 7, we are going to have 6. So this number here lies in between 5 and 6. So it must be 5 point something, right? It must be 5 point something. So that is to say the greatest integer less than or equal to this sum of these two integrals will be 5. Because for it to be 5 point something, the greatest integer will be like truncating the number and giving us just the whole number, which is just 5, right? So this right here is the greatest integer, which we denote it as this of the sum of those two integrals. Let me just put it I here to be 5, right? Okay, all right, thanks for watching, and please share these videos and subscribe to my channel.